All right. Well, thank you very much for the introduction. Thank you, everybody, for showing up. So when I was trying to think of a good name for this presentation, I knew I wanted to talk about performance optimization. I knew I wanted to talk about just how to make databases faster, data-driven applications faster, whether that processing is happening client-side, server-side, or in the database. I came up with a list of a bunch of different titles. And at its core, what I was really trying to get at is this is not that hard and it's not black magic. When we look at performance optimization, everyone thinks it's magic. Okay? It's because they don't know it, they don't understand it, but it's really at its core very, very simple thing. So it's not magic. We're not going to talk about any tricks. We're not going to talk about any secrets. And I looked on Harry Potter World and I couldn't find a spell that made things go faster. So yeah, there are no magic spells to make things go faster. It comes down to hard work. It comes down to discipline. And believe it or not, a whole lot of creativity, which I'm going to talk about more. So performance optimization, it's time consuming. Yeah, sometimes it is. Is it frustrating? Usually. And is it rewarding? Absolutely. Basically, those describe software development in general. That anything software development is going to take more time than you expect. It's going to be more frustrating than you expect. But when you get it working, you're like, yeah, it's the best thing ever. It's really, really rewarding. So the objectives of this talk, I also wanted to try and focus on a couple of different levels of developers, because I know there are junior developers here, I know there are senior developers here. So for the junior developers, I wanted to be able to introduce the mechanisms of performance optimization. What are the mechanisms that affect performance? What are the things that you need to be looking for? Then second, understanding the process of tuning. I've got a performance problem. What process do I go through to tune this to try and make this thing go faster? I'm trying to target that more at junior and senior developers. And then for people who have been through this process before or about to go through this process, I'm going to provide a set of tips. No tricks, because there are no magic spells to the whole thing. I also thought about what technologies would I want to demo. Do I want to do Python? Do I want to do SQL Server? Do I want to do Mongo? And when I really thought about it, and my experience has always been that performance tuning, the concepts are really universal. That once I got good at optimizing one thing, say Microsoft SQL Server, and I went to MongoDB, I thought I'd have to relearn all that stuff. I didn't. I actually wound up taking a lot of the same mental constructs, applying them a little bit differently, but still thinking about it the same way. And I wound up encountering a lot of the same issues that I had in SQL Server in MongoDB. Now, made some things easier, but also made some things harder. There were definitely different trade-offs, but a lot of the concepts crossed over. And I've noticed the same thing across different programming languages and different paradigms. So if I'm doing object-oriented or functional, again, I'm kind of thinking the same way. Applying it differently, because it's a different paradigm, but I'm applying a lot of the same concepts. So when a lot of people talk about performance, especially nowadays in cloud computing, they're also thinking about scalability. So when I say performance, I'm usually referring to make one thing go really, really fast, like a single-threaded process, make that go as fast as possible. Then we have scalability. That's, I want to do many of those things all at once and hopefully not slow down too much for all of my users. With scalability, you're always going to have some degree of slowdown. The idea is you're trying to control that scalability curve. But at the end of the day, users don't care about performance versus scalability. Their experience is going to be the performance of doing that one thing in the context of a million other users trying to do that same thing. So their experience is always kind of that performance and scalability. So I will cross back and forth, but again, a lot of the concepts are very similar, that when we deal with certain performance issues, we can take that same concept and apply it to scalable. So first I'm going to talk about mechanisms. So can anybody identify the performance problem with this bicycle, other than that it's a fixed gear bicycle? How many people in Asheville am I offending in that one? There's no derailleur. There are no gears on there. Yeah. So what's the performance problem on this bike? It has square wheels, right? So some performance problems are pretty obvious. What's the performance problem with this? Square everything, exactly. It's not very aerodynamic. So when we look at the physical world, a lot of times we intuitively understand what the mechanisms are for performance. But when we look at those mechanisms, we need to look at them within the context of the environment that it's running. What if that big boxy truck is driving through a vacuum? Is that a performance problem? No, we just changed the environment. There's no air resistance. In computers, we're looking at certain computer resources and we're looking at data structures. So the environment is there wind resistance? And then the structure is it a wind resistant friendly structure for that environment? So if we look at computing resources, we start looking at all the different things that can slow us down. So allocating and managing memory is expensive. We normally don't think about it, but if you start doing things a few billion times, memory allocations start to become very important. Garbage collection, expensive. Threading is expensive. Disk is expensive. Serialization is expensive. Network is expensive. And accessing your database. Those are all expensive performance hits. So the only cheap free thing I could think, or anything that's currently loaded into the register, that's free. But anything else is going to cost you some kind of performance. So looking at the types of data structures, there are really only a few when you really think about it. When you think about the classes of data structures, each one of those classes may have hundreds of different variations, but they're all very similar. First is a linear data structure. That could be a linked list or it can be an array. So it's real simple. I have a list of things and I want to find something in that list. The only way I can find something in a linear list is start at the beginning and go through it. Okay? Whether that's a linked list or an array, I still have to go find it. Now, if it's an array and I happen to know the address, yeah, I can jump right to the address. That's typically not the problem you're solving. Another one is a hash. So a hash is really good when you know the key that you're trying to look up, and you're trying to find that one key of something that you're trying to look up. So think of a dictionary. There's one entry for a word in there, and if you know what the word is that you're looking for, you can find it very easily. Next is a tree, and this is probably what's used the most, especially in databases, to be able to find things, because with trees, they're very powerful, very flexible, lots of different things that you can do with it, and typically you're using it to search data. And in that case, you could be looking for one thing, or you could be looking for a range of things. So I want to find everybody who has a salary between $50,000 and $70,000. I'd want to use a tree for that. I couldn't use a hash because on a hash, I'm looking up one thing. I could find everybody who has exactly a salary of $60,000 real quick. But if I'm looking for a range, then I need something like a tree. And finally, a graph, which is if you're trying to find associations between things. You have all these different nodes. So then there's the structure of nothing. There is no structure. There's essentially chaos. So in this example, where she's got this pile of paperwork behind her, essentially she has no structure for the data that she's managing, which means it takes a very long time to find something. You can really think of it like a linear search. She has to go through every single piece of paper in that stack to find what she's looking for. Now, if she's looking for one thing and she finds that one thing, she can stop. But if she's looking for every invoice for customer ABC, she doesn't know when she's done. She has to look through that entire pile to find things. So very, very slow searches. So is there a benefit to a chaos structure or no structure? They're really fast to insert into. That's why that pile developed. Anybody's office, it's very fast to just say, oh, I'm just going to stick that on the pile really fast. I didn't have to file it or anything like that. I can't find it again, but it was real easy to add to my pile. All right, what about when you're updating data? What do you guys think? it's terrible from the perspective of first you have to find the thing that you want to have to update. Deletes would apply, the same thing would apply to a delete, is that in order to delete something, first I have to find it in the pile, then I have to throw it in the trash. So it's always going to be limited by how fast you can search for something. So let me give some good concrete examples that don't require code. I had to look really hard to find one of these. And you can see how thin it is nowadays. And this is the Asheville one. I live in Weaverville, and it's like a pamphlet. So this is actually the yellow pages and white pages. And everybody knows, even if you've probably never used one, I don't know the age of everybody in here, but you know basically how to use the thing, right? So I'm going to look up a name, and I'm going to use my knowledge of the alphabet to try and find something as quick as possible, right? So I'm going to look for a plumber. Okay, P, that's kind of near the middle of the alphabet. So I'm going to open it up generally to the middle and see if I can find that. Okay, I'm looking at some M's, so I know which direction to go. Okay, I can flip a couple pages one way or the other. And what was interesting is when I kind of looked at the middle here and said, okay, what's about the middle? It's not an M, which I was expecting. I was kind of expecting an even distribution. It's kind of more like the I's and the F's. And then I started flipping through. I'm like, okay, it's front-loaded. There are a lot more ads in the front of the yellow pages and the back of the yellow pages. And I started flipping through. It's all the attorneys. They're just pages and pages of single-page ads of attorneys, and they're kind of bloating the front of that. So basically, the algorithm I go through for searching a phone book is a tree. This is a tree, not made from trees, but I'm searching it like a tree. And I'm using, what's that?
It is actually made from trees.
It is made from trees, but I'm using essentially a tree algorithm for searching this thing, where I'm starting in the middle and then saying, okay, do I go left or right? Okay, and then I go here, okay, do I go left or right? Then eventually I find the right page, and then once I'm on the right page, I have to find the right entry. So we have several key concepts that I'm going to be presenting here, and key concept number one is partitioning. And it's essentially understanding your data and how best to organize it. So here's a visual example of essentially how the tree structure works. And again, when I drew this, I wasn't having a phone book in front of me, so I figured M would be the logical partitioning. But if you imagine here we have nodes that we're traversing, and we essentially ask the question each node to say, okay, is it at A or after A, but before M? So basically, is it between A and M or after M? Okay, well then I get to hop to here, and then I get to hop to here. So you can see that I don't have to do a linear search. I don't have to look at 26 things to find the one letter that I'm looking for, or the one entry on that particular page that I'm looking for. I can hop very efficiently to what I'm trying to get to. So I'm going to do a quick demo, and there's not much you have to look at here because I understand this is very small. But what I will do is make sure to explain to you what's happening here. So for my demos, what I'm doing is I'm using SQL Server. And I'm also going to record my screen since we started that and then restarted it. Okay. So in here within SQL Server, like I said, we can apply the same concepts to any database, to any language. SQL Server is nice just because I can put a ton of data in there, and it already has all the algorithms built in there, and it gives me a lot of transparency into its thought process for finding the data that I'm looking for. So the first thing I'm going to do before I run any test is essentially I'm clearing cache because I don't want that to bias my test for demo purposes. So the first thing I'm going to do is I'm going to say, what if I have a table that has no indexes on it whatsoever? It's that chaos structure. It's just a pile of stuff, and I'm trying to find some data in there. So if I run that query across a table that has 10 million records, say how many records are in there? 10 million. And then what I can do is I can look at how long this took 6 seconds, and I can also see how many physical reads were performed. So there are physical reads and read-ahead reads. This is SQL Server being very eager in the way that it retrieves things, but essentially it's a physical read from disk. It had to look at 198,000 pages in order to even just give me a count of how many records were in that table. Now, what if I'm looking for something with a particular ID? I'm looking for a member ID. So this is a members table. We have members of a user group, very large user group of 10 million users. And each member has an ID. And so I'm looking for a particular member by ID. And the question I want to ask is, or I just want to be able to find that particular member. So if I do that, I'm clearing my cache. Fixing my typo. And I'm running the query, and it's taking a very long time to find one record. But to find that one record, it took 3.7 seconds, and it performed 198,000 physical reads off the disk. Okay? So it's behaving very much like a linear structure, linear data structure. Okay? Just like the yellow pages, it didn't know anything. So it started at page 1, go plumbers, plumbers, plumbers. Did that 198,000 times. It's very, very slow.
How big of a block is it reading? You know?
It would depend on, I think there's a default page size, which I don't remember. It's been so long since I've looked at it. And then, of course, it would also depend on the record size, which I have no idea for this table. But the point is, we don't even want to care about that. We want to be able to get to the point where we don't have to look at 198,000 pages, regardless of how big they are. We want to look at as few pages as possible. So I just ran the same query in a different table that happens to have a primary key on it. It has a clustered index, which I'll explain in a second. So instead of doing 198,000 reads, it did 4. So it looked at 4 places on disk to be able to find that data. And it did that in 6 milliseconds. Okay, that's not cached or anything like that. So, it's a fast solid state drive, but it doesn't matter. What really matters is how many physical operations had to be performed to be able to do that. So that's demo 1. I'm going to come back to that same idea and kind of build on that a little bit. But I'll continue with the presentation and set that up. So what we did is we looked at essentially querying for unstructured data or flat data or that chaos structure, basically something that's just in a linear random order that required the reading of all data to answer a simple question versus a tree. And the difference between those two tables, one didn't have any indexes on it at all, didn't have a primary key. Once you add a primary key to something, that's called a clustered index. And that is physically how it's stored on disk. So, question, the yellow pages. What is the clustered index for the yellow pages? What's that? Well, what about the record is showing up here? Is it the name or is it the category?
The word in the corner that, that tells you what's on that page.
Correct. And so for the yellow pages, what we're looking at is the topic. Attorneys, plumbers, roofers. Okay, that's the clustered index. It's physically structured that way. Okay, all the attorneys, well, the attorney's a bad example. All the plumbers are all on one page. Okay, the white pages are up front. Different clustered index. Still alphabetical, but it's a different data field that it's looking at. It's looking at the name of the company. So the clustered index on that case is the name, and the yellow pages is the topic, the subject, whatever their profession is. So the primary key is rarely what we want, rarely what we're looking for. In the case of the member ID, we don't really care what the member ID of somebody is. What we're really doing is we're looking up somebody by name. Okay? So, okay, it's already physically structured by member ID, so let's do a table scan. But we can't, that's really too slow. So what do we introduce? We essentially introduce another index on top of that, another tree. So think of this as the index at the end of a book, a reference book. Everyone reads computer books here. At the end of that book, you're going to see an index to be able to show you a secondary way of looking up information. So the primary way is you're going to look at the table of contents, you're going to see the subject, because that's the physical structure of the book by chapters. But then you want to cross-reference that using the index at the back of the book, which would, in technical terms, is called a non-clustered index. And so let me go ahead, I'll just jump to my demo. So just to make sure I don't have that. Nope, that one's already gone. So what I'm doing is I'm looking up anybody who has a last name that starts with S. This is a SQL wildcard, just S %. I look at my statistics, and I can see that it did 204,000 reads. Now in this case, it actually did more reads than the other one. Now the difference is this little compiler hint here, which I'll explain in a second. Oh, I know why. So in this case, what it had to do was scan all the data and look at more information than simply the primary key. Because what I was interested in was the last name. So as I'm reading through this, let's say I'm looking through the white pages, and I'm scanning through. Oh, I found it. Okay, great. So I found it, took a bunch of reads to be able to find the particular business that I'm looking for. Oh, but now I need to go look at phone number. Okay, so essentially what we're doing is we are asking the white pages, let's go find somebody with a specific phone number, which means we have to do a lot more reads than we were originally expecting. So in order to handle that, we create a non-clustered index, on this case, the last name of a member. And now what it's doing is it's indexing 10 million records. And this takes 20, 30 seconds, something like that. And when it's creating the non-clustered index, think of it as creating an index in the back of the book, where what it has to do is go find all the data that's in there, and then essentially find the page number or the address, that specific location where it exists, and then of course it has to store all of that off. So building an index is a very, very expensive operation, as we saw. So here I'm going to make sure I'm clearing my cache. And then I'll run this query again. And you can see it happen very, very fast. Oh, it's still running. But in this case, instead of 200,000 reads, I did 2,748. So substantially less to be able to find that. Now in this case, I'm doing a pretty non-specific search. I'm saying just give me everybody whose last name starts with S. A lot of records that we have to look at. If I go ahead and count the data, I can count the data just as fast, but we're still having to go out and do essentially the same number of physical reads. Let me go back to the presentation, and I got one more demo to show you after this. So indexes are great. They make everything go faster, right? No. The reason is because there are lots of costs of indexes. Remember, everything costs. Everything's expensive. So indexes, there's time required to maintain these indexes. There's disk space required to access these indexes. Every time we look things up, there's going to be a cost associated with that. Even if it's going to be saving it in the long run, there's still costs associated there. So the more indexes you have on a table, the slower your writes are going to be to that table. Because every time you write new data to your table, you need a place in the index. So imagine if you have a book and then you just added a new subject to the book. You then have to go to the index and make space in that index for that new subject. So first you need to find the place to insert it in every index in the table. So anytime you're inserting new data, it's got to update every single index. Okay, I found out where it goes in every index. Oops, there's no room. That index is full. What do I do? Key concept number 2, fragmentation. Everyone has probably had fragmented hard drives before we had solid state. Basically, just things get so disorganized that they start to lose their efficiencies. They're not optimized anymore. So you've created a nice filing cabinet and you populated it well, but then you ran out of room on your filing cabinet. You just started stacking things on top. So the value of that filing cabinet, the ability of that filing cabinet to yield better performance dwindles real quick. So the point here is knowing how your data will change and leaving room for it to grow. And that can require some experimentation. Important thing to remember is databases are not static. If you write code today, Python code, C# code, C++ code, it's going to work the same way 10 years from now. It's not true of databases because databases are growing, they're shrinking, they're changing shape over time, and a lot of times they grow in very unexpected ways. Business that is being driven off of this database suddenly has a very different distribution of how they access data, or how, in the case of the attorneys, right? What if we didn't have attorneys? Okay. The book would be smaller, and the book would definitely be distributed differently, right? Suddenly they invent the profession of attorneys, and attorneys like to advertise a lot, then the structure becomes very different. So when we're doing tuning, and here's where I'm going to start to get into the process of tuning, it's all about trade-offs. And what you're trading off a lot of times is how fast do I want to read data? How fast do I want to write data? How much disk space do I want to use? And an important one that a lot of people don't think about until it's too late is maintenance windows. Software needs to be updated. Databases need to be backed up. Databases need to be re-indexed. There's maintenance that has to happen on these systems, which quite often can lock things up, can put a slowdown on the system. So perhaps your requirement is the maintenance window needs to be very, very small. Okay, well, I may have to trade off some read speed, write speed, or disk space, or something else, or just buy lots more servers to be able to get my maintenance windows as small as possible. Key concept number 3, tuning equals trade-offs. Don't be a purist, be pragmatic. So I'm going to look at one more demo, and then we're going to focus solely on kind of tips and the process after this. So remember I said I liked SQL Server from the perspective of I have a really nice transparency into the decisions that it's making. So what I can do is within SQL Server, this tool right here is my friend, and the primary tool I've used to figure out how SQL Server is making decisions and how bad my design is based on the query plan that it develops. So what I'm doing is I'm running a query that we saw before, but what I'm looking at this time is the query plan or the execution plan that it produced. So it's essentially telling me how it went about serving that particular query. So in this case, it's saying that it used the clustered index to try and find that information. Now, what seems weird about that? Because we're looking something up by the last name. Why does that seem weird? But my point is on this, most people, when they see clustered index, they're like, oh, clustered index is fast. I'm glad that it chose the clustered index as the primary way of looking this up, because that's the fastest way to look something up. However, my clustered index is my member ID, and I'm asking for last name. What SQL Server did right there is it said, okay, I know I have an index that looks at last name. However, you're asking for, it looks at more than just the where clause. It also looks at the select clause and says, okay, well, I can find everybody whose last name starts with S really fast, but that's not what you asked for. You asked for entire records. So the most efficient way for me to give you all those records is actually to scan the entire table, so that way I'm already looking at the clustered index and I've got that record right there and I can return it. So instead of doing a two-step process, it's essentially doing it one. So like I said, this has been a primary way of telling me when I've written bad code. I've written a bad query or a query that's not optimized. Now, I could add some more indexes, or I may look at my business problem and say, but I don't really need all of the fields in that table. What I need is just the member ID, the last name, and the birthday. I don't know what business problem this is we're trying to solve, but that's what we're trying to do. So if I run that query, oops, still waiting for the query plan. I run that query, that's the query I want to run, and still hit the clustered index, but it makes an interesting recommendation to me now. And says, well, you know, if you're just looking for these three fields, you would benefit from creating an index. Creating an index that just has those three fields. Maybe it's sorted by last name and then includes those other pieces of information. So I already have that index queued up, ready to go. So what we're doing here is creating an index just like we did before. It's the exact same index that we had in the previous demo by last name. But in the index, we're adding some extra pieces of information. The way I like to think about this is indexes, like I always like to think in physical or visual terms. And so I'm always imagining a whole bunch of index cards and I'm laying them out on the table. And the question is, what do I write on those indexes to make my search as quick as possible? So if I were to write on those indexes just the last name and then an address of where to go find that other information, I'd have to first go find the thing in the index and then go to my other place to find it. But what if in the index card itself, I just happen to write the member ID, the last name, and the birthday? Then there's only one place in the whole database that I have to look to be able to find that information, and it's less work that has to be performed by SQL Server. So now if I run this and look at the query plan, you can see that it decided to make a different decision this time. The decision that it made this time is to search for an index and is looking for, it's using the index that I just created, because the query optimizer looks at all your data, looks at all your indexes, looks at your query, and tries to make a really intelligent decision about the best way to leverage all the resources that you've already allocated. And in this case, I just happen to know that it's going to make the decision to say, I'm going to look it up by last name and use that index that also happens to store the member ID and the birthday. Remember, we had that other index that just had the last name. And it was smart enough to realize that wasn't going to satisfy the entire request. The entire request being give me member ID and birthday. So the point there is looking at your entire query, looking at the query plan, and doing a sanity check against what you think it should be doing and what SQL Server is actually doing. And the solution is quite often not creating another index or reorganizing your index. Sometimes that's the right answer. A lot of times I've found the right answer is restructuring my query, restructuring the way I'm asking the question, and suddenly SQL Server becomes very efficient. And this kind of crosses across any database or any language in that, yes, the data structure is important and how you populate that's important, but also understanding how you're going to use that. So the algorithms that are being applied to that and making sure that there's a nice fit between how your data is organized and structured and how you're actually querying it. So we talked about all that in the demo. I'm going to go to, so with any index, there's some maintenance required. Now, a lot of it, databases will handle for you automatically, but it's important to know that it happens. Whether it's happening in real time and taking longer to commit, or it's delayed, so there's less consistency, like things like Mongo, where you get the data in there right away, but your index might take a little while to update. Or you may choose, okay, I'm going to let it get out of date or get fragmented after a while, and on a weekly basis, I'll go ahead and re-index to reorganize that. There's maintenance involved. So let's say, it gets fragmented, you want to rebuild every index, or rebuild your indexes every 15 minutes. No, because there's an expense to that, and it will wind up locking your table. So again, trade-offs. These are the different things that all have to be balanced out. I'll talk about one last way to be able to partition. And this is a kind of an interesting technique. I've always called them snapshots. I think before they had names, they're now called materialized views. But imagine all I'm interested in are plumbers, okay? And imagine that the plumbers all show up on a single page, and I don't want to carry this thing around with me, okay? There, I just took a snapshot, okay? It's a picture. Essentially what I did is I created a copy of that data that I can then access a lot faster. So I don't need the bulk of all this thing. Now, it's out of date. As soon as the next phone book comes out, this is not very valid anymore, but it's a lot faster and easier to use in the meantime. So the technical term for this is called a materialized view. Basically, it's a query that you then sort of take the results and store it off somewhere. And you would typically have a table or structure that you're writing to really fast, okay? So this is my structure, but then something else that I'm reading from. So in the case of databases, I might have one table that's really fast to write to, but really slow to read from. And it always has the latest data, but it's really slow to read from. And then I have another table that gets created every once in a while from that I can periodically rebuild, read really fast. I'm just willing to deal with some stale data. Now, that's expressing everything in SQL terms. Now, NoSQL made this exact same decision. You look at things like Mongo, they said, yep, you can insert as fast as possible, but you're going to give up some consistency, meaning that some of your reads may not return the same data that you just wrote here as fast as possible. So again, these concepts still exist. Some of the terms change, but the concepts just sort of move around a little bit, but they're still there. So in summary, there's different ways to partition data. We could use indexes. We could partition by write versus read. So I want to write to one place, read to another. That's a materialized view or a snapshot. I could partition across tables. I could say, okay, I'm going to create a table for this sales region and a table for this sales region, and a table for this sales region. I can partition across disks. That's essentially what RAID arrays are for, or you can also break things up differently into different file groups on disk. So maybe you have ways to be able to break up your database so that you say, okay, I'm going to write a particular piece of data to this part of the disk and other pieces to here because I know that they're both hotspots and I don't want to put them on the same place on disk. We can partition across servers. Okay, this is where we take a database and we just spread it across lots of different servers. Again, maybe the sales region idea. We pick one sales region and put it on one server, another sales region, put it on a different server. Nowadays, we can even partition across data centers. Okay, I'm going to take all my data that Japan needs and I'm going to put it in a data center in Japan. I'm going to take all the ones that Germany needs and put it in Germany. And so I can partition those different ways. So the point is thinking about partition and then just thinking about at what scale do you need to be able to partition. So this is where performance and scalability really overlap, is that the key, in my opinion, to getting really good at scalability is just taking the data and being able to figure out creative ways of breaking it up and partitioning it so that you have as many workers doing work as possible. And those workers could be different tables, different disks, different servers, different data centers. Generally, this is the order that I would sort of deal with things. You know, first I would make sure I got really fast disks. Then I would make sure I got some good indexes. Then I might start doing some advanced things like materialized views. Might even change the way my clustered index works. I do that maybe once per project. There's a good use for it. The way things are organized by files might break things up across tables into partition views or federate or break things up across data centers. Okay, so when we get into the actual process of tuning, it's real simple. Run a test, analyze and record those results, make some changes to your code or database, and repeat. It's just an experiment. Okay? Key concept number 4, start thinking like a scientist. Start thinking like experiments. How am I going to structure these different experiments? What am I going to monitor? How am I going to know when I'm done? How am I going to know what success is? Because fast is never fast enough, so you kind of need to agree ahead of time, you know, how fast these things are going to be. And you don't know where your bottlenecks are up front. You may have some guesses, but decide up front what resources you're going to monitor, CPU, network, disk, wait queues, you know, things like that. And very important, make sure you're figuring out how to save that information off, record it somewhere. Okay, this is where you put your scientist hat on, and scientists are very good at keeping good logs because they will need to go back and be able to answer the question, why was this test better than this other test? And be able to compare those things side by side. Work in a dedicated performance environment. Okay? This is becoming easier and easier. You don't have to, you know, in the world of the cloud, where you can just stand up new cloud resources and say, this is my performance environment. Team, leave me alone. I get to play with this all in my safe little space. The nice thing about the performance environment, you don't need it for the entire course of the project. If it's a year-long project, you don't need to stand up all those resources for a year. You may need it for a couple weeks. You may be using a lot of resources for those couple of weeks, but you don't need them for that long. So, budget. If performance is important, talk to the people who are writing checks and tell them we need a budget in our cloud resources to be able to do this. If you're not running in the cloud, say, hey, we need a budget or at least server time sliced out somewhere where you can safely run these performance tests in isolation. Because if you're running them on your typical development server, you're going to be aggravating either the other developers, your testers, somebody you're going to be aggravating. And you're not going to get very good results because you're not going to be able to have a nice, isolated, controlled environment. Here are some other tips. Creating a mechanism for resetting data back to baseline. Okay, if you're going to do an experiment, you want to make sure that they're controlled experiments. So you want to make sure that every test that you run, that of course is probably going to be modifying data in the database. How do I get data back to the same baseline each and every time? So that could just be as simple as a backup and a restore, or it may be more complicated. It depends on your situation. But just make sure that you have a way of being able to do that. This is something I've started doing in the last couple years where at the beginning of a project, I figure out how to generate a lot of data, meaningful data within the problem domain. There are some, obviously I want lots of data to be able to test against. I don't always have lots of data at the beginning, either because it's a new project, so the data doesn't exist, or I'm porting over the data and it's taking so long to clean up all the crummy data to get it into the new system, I can't wait for that. Or I might want to say, well, what happens if the data is suddenly 10 times larger? So I want to be able to answer those types of questions. So what I'll do is create lots of code or scripts up front that can create meaningful data. And when I say meaningful, things that if they were presented in a UI, a tester or a product owner would look at that and say, I know it's bogus data, but it's reasonable. Okay? Things are sort of reasonably associated with each other. And I found that there are a whole bunch of benefits to creating all of this data. So when you have your UI developers working, they actually have data to look at. So they don't have the 4 manually entered records, they now have 300 records or 300,000 records, and they can bump into those issues in the user interface earlier. Integration testing. So if I'm writing not unit tests, but integration tests, I want to be able to test my queries against data of different size. I can do that against data that's already there. Loading performance. By this I mean, okay, I'm going to start with a blank database and I want to be able to load massive amounts of data. Again, I might have data that I need to import at the end of the project and they're still trying to figure out how to clean up all that crummy data. In the meantime, I need to figure out a way to quickly load lots of good, clean data in there. So that's been beneficial to me in the last couple of years. And last, a lot of times in big projects, there needs to be a training or demo environment. So you create this line of business application and they say, okay, we now need to train our 50 salespeople on how to use this stuff, and they don't want to train on the production data. They don't want to train on the dev data. They want fake data to be able to test on, to be able to train on, to be able to play, break, and easily reset to get back to there. So these are all the side benefits that I found to putting that investment up front. Another tip, feature flags. The ability to turn off certain parts of your application that would be harder than simply commenting out. Okay? The 2 that I always put in there, security and logging. Okay? Because a lot of times security is my performance bottleneck, permission checking especially. And it's nice to be able to say, what if I just take that out of the equation? What if I just take security out of the system? What does performance look like? Oh, it's still really bad. Okay, it's not a security issue. I can put it back in. That's one of those things that's also a nice side benefit because it takes a while to get a security system up and running. And I've been in situations, been in projects before where we're getting the security system up and running. It's integrated in the system. The developers can't work anymore because the security system has a bug. It's nice to be able to turn off that security and get back to work. Logging is another one of those. Surprisingly, I've never actually been able to trace a performance problem back to logging. It's one of those things I always expected that would be a performance problem. I mean, if I sat in a loop and just logged, I'm sure I would, but under normal circumstances, I've never been able to trace a true performance problem back to logging. If anyone's concerned about that, the security, turning that off, what I have done is compile time switches. So that way in my debug versions, I can turn that off, or in maybe a performance version, I can turn that off. But anytime the build server actually builds a release version, it always includes security. So don't want to let any holes creep in. So I remember I said when we're doing these experiments, we need to put on our scientist hat, so taking notes along the way. Because a lot of times you'll do experiment, make some changes, do experiment, make some changes, and you start going down a path thinking this is the right path to try and get the best performance. And then you realize, no, that's a dead end, it's a problem, or I introduced a problem somewhere along the line I can't resolve. I need to back up 7 steps in my test, pick up from there, and sort of spawn off a different approach. So the ability to be able to reconstruct a test at a later time, come back and spawn off from there. Don't trust any one test because this is performance. These are computers that are doing other things. Network is doing other things. The database might be doing other things at that particular time. So just because you run one test and it's better or it's worse, don't trust that. Run it a couple of times under different environments to make sure. Again, if you have a dedicated environment, a little less of an issue, but I have hit weird issues where if I run the same thing 5 times, I've gotten very different results. All right, here's probably the most important one. Be ready to refactor. If you're going to fix security problems, it means you need to fix code. It's very rare that you're going to be able to fix 3 lines of code and suddenly get great performance. You're going to have to be looking at a whole bunch of different code, probably across a whole stack, all the way from the UI to how it's being serialized, down to networking, to database. You might have to make changes across all those stacks to get the performance that you need, which means you might be dramatically refactoring and reorganizing your code. If that sounds painful, then you're going to have a big problem in your project trying to get the kind of performance that you want. So as you're designing, think about refactoring. Think about getting the tools in place and get some people who are really good at being able to refactor that. If you're using something interpreted which is not compiled, fine. Of course, since you're interpreted, you've got lots and lots of unit and regression testing, right? So you could be running a lot of regression testing to make sure that you're not breaking things as you're making these changes. So key concept number 5, good design gives you more and better options. So the better your design, the easier it is to refactor, the more options you have. If you're doing these experiments, you're doing this tuning, and suddenly you have this aha moment, that's the fix. Oh, that's going to take a long time to make that change. You know, that's a very demoralizing place to be. So think about good design. Good design pays benefits over time. Yes, there's a higher investment up front, but lower total cost of ownership as you're going along. So regarding design, things that I've noticed is working within the paradigm. Okay? If you're writing stuff in SQL Server, write in the relational paradigm. Don't write stored procedures. That's the procedural paradigm. Write in the relational paradigm. If you're object-oriented, get really good at object-oriented design. If you're writing in functional, get really good at functional design. And the reason is don't misuse a tool and then say it's not working right or I'm not getting the performance that I want. I see all these comparisons between these different languages that are different paradigms, like for example, C# and F#. Which one's faster? Problem is when they do comparisons, a lot of times they're taking C# code and implementing exactly the same way in F#. One's an object-oriented language, the other's a functional language, and say, oh, it runs so much slower. They're using it wrong. Suddenly they do it idiomatic, which means writing it in the paradigm, they get good performance. Choosing your data structures wisely. I think we've talked about that a lot. Think about where your data is going to live and where it's going to be processed. So by that I mean, is the data living in a database? Is it living in SQL Server or is it living in MongoDB? Is it living in this data center or a different data center? When we get that data, are we going to process it in the database or are we going to process it server side? I think those are obvious, but as people are moving across different tiers, sometimes it's hard to remember that there are options there. You don't always have to do everything in the database. You don't always have to do everything server side. You do have some options there, and sometimes intuitively you might think it would run faster one place or the other. Run an experiment, try it. Design for change. That's the whole refactoring thing. Design for performance from the outset. That's what I meant to say. Design for performance from the outset. So from the very beginning, think about performance. It's very hard to optimize bad designs because once you get into that bad design, you're having to deal with that bad design and every little change you're having to make. But don't tune too soon. So this is a question I get asked a lot. What's the right time to start tuning? As late as possible. Here's the process. First, make your code work. Second, make it work right. Make sure it's actually fulfilling all the business requirements and the product owner is nodding his head or her head and saying, yeah, that looks right, but it's slow. Okay, then start working on making it fast. Okay? When we're building a table, we don't put the finish on first. Okay? We get the table working, we get the table structure, sound, and then we put the finish on and we polish it. Okay? That's essentially the way you should think about performance tuning too much. You might do it a little bit throughout, but before you put that last polish on, you want to make sure that everything's right. Now, with that being said, make sure you allow enough time before the deadline to actually get this thing done. Don't wait until the last minute, because it can take a lot longer than you think. You can get lucky. I've gotten lucky a few times, but other times it just takes a lot longer to tune and figure all this stuff out. And then the third concern there, the third attribute to deciding when the right time to start tuning is how freaked out the product owner is getting. Because at some point, the product owner is looking at these releases and saying, it's working right. Boy, it's slow. Users are really going to be unhappy. And for a little while, the product owner will understand. Oh, I know you guys are still working on it. But then as it gets closer and closer to deadline, they get more and more freaked out. So manage expectations. Let them know ahead of time that, yes, we're going to deal with performance. We're going to deal with it later. That's tough sometimes, but at some point, they will get freaked out enough that it might get moved up into the project plan, and so be it. So ideally, you do it as late as possible, but there are always political concerns in there that sometimes you've got to tackle it a little bit earlier than you want just to make everybody happy. The reason why you want to wait as late as possible is because you are restructuring these things quite a bit. And it's nice to be able to restructure correct code and design code and fully tested code and fully regression tested code. If you don't have all this regression testing and you're not confident in all your regression testing, it's going to be really hard to convince the rest of your team, I'm going to tear this whole thing apart and make it a lot faster. And then the next question is, well, what'd you break? You want to be able to answer those questions by making sure that the project's at a good place to easily answer that question. So some suggestions. A lot of times when I'm talking to people when we run into performance, the first hammer that they reach for is caching. Let's use caching. Well, that'll make it run faster. Sometimes that's the solution. But that's the first hammer that everybody reaches for. Let's cache. I was trying to pull people back a little bit. And the reason is because you need to start asking some fundamental questions. Am I going to be able to fit enough in memory to satisfy my requirements? How often, what's my cache hit ratio? How am I going to invalidate cache? It's like the hardest computer science problem in the world is trying to keep your cache up to date and modern with the current data so that you're not having stale cache. So again, it's great. Definitely a tool in the toolbox, just I see people reach for that too soon. Another suggestion, all databases, all languages, they have weird performance quirks. They're usually well documented. You know, in the .NET framework, which is the world I come from, strings. You know, that's one of those quirks that you have to understand how memory is allocated to strings, otherwise you can create this really bad performance problem without even realizing it. All right. Here are some personal experiences that I've had. I'm not saying these are universal truths. I'm not saying these are things that you're going to hit. It's just these are things that I've hit, and it seems to be really consistent. I've always been surprised that I don't hit an issue in logging, and I'm surprised that I don't hit a performance issue with SSL. You know, we're always doing development, and then at some point we go, oh yeah, we need to put an SSL certificate on there. And I'm like, oh, is that going to kill performance? It never seems to. So somehow they figured out how to make SSL fast, good. And logging, most good logging frameworks are non-blocking. So I've never run into any issues with that, assuming I'm not.
Write all the anyhow.
Exactly.
You're just writing, you're not.
Exactly, yeah. So you'd have to do something really weird, like just sitting in a tight loop and logging 10 million things all at once. But it's one of those things that when I first started logging, I just always assumed that's going to be a performance problem. I need to keep an eye on that, and it just never has. The things that are performance problems that I'm always surprised by, even though I say it every single time I hit them, I'm like, really? Is memory allocations. You know, it's like memory, it's fast, it's cheap, it's got to be really fast. You know, I'm not hitting a network, I'm not hitting a disk, it's always going to be the fastest thing available. You know, I always want hitting some kind of memory allocation issue that just make a tweak and it's a lot faster. So it's one of those things that's just very easy to overlook. Serialization. Remember, anytime you send something over the network, like a database call or the database results coming back, you're dealing with serialization in there. You're going from the native format that it's there, you know, in let's say SQL Server. It has to serialize it, has to send it across the wire, then you have to get it and you have to deserialize it. There's a lot more I've seen a lot more performance hits in serialization than I've expected. Again, it's one of those things I know and surprised every time I hit it. Threading and locking, those are kind of two sides of the same coin there that a lot of times, just like caching, it's one of those tools you reach for. Oh, how am I going to make this run faster? More threads. You know, I've got these multi-core processors. I'll just do it multi-threaded. There's costs associated with that. Managing all those threads, merging all those threads back together, and then, of course, the resource locking associated with that. Some common hotspots that I've hit. So a hotspot is a place in the database where you might have locks. So let's say Thomas and I are sitting here and we're both trying to use the phone book at the same time. Okay, how many of us can use this phone book at the same time? In this case, one. So somebody's got to sit around and wait. Okay, that's a locking issue. There's one resource that only one person can access or one resource can access at a time. So now that's a simple example because it's one resource, two people, but there are other times where something just has to be accessed so many times, so often, that it becomes a hotspot in the application. The ones that I've hit, permission checking, especially in the last couple of years, different businesses that I've worked with, they create these very large, complicated permission systems that say, okay, well, this salesperson or this person with this role, which could be a salesperson or a sales manager or CEO, has these particular rights to these particular things in these regions, but not these other things. So they wind up creating these very complicated business rules about who can see what when. Well, all of that has to be turned into data in the database representing who can see what when. And every single time you request data, you need to run them through all those permission checks. So within the last few years, I've been seeing a lot more of that complicated permission checking, that becoming a hotspot, and having to spend a lot of time performance optimizing that. And then every application, this is kind of what I call the center of the universe. Any application that you write, there's kind of always that center of the universe if you look at a database design or whatever. So in the case of an order entry table, your order entry system, the table at the center of the universe, the object at the center of the universe are the orders, customers and orders. If it's a CRM, a customer management system, those might be the customers or it might be the contacts with the customers. There are certain tables that are just the center of that universe and everything's sort of built around that core concept and everything else is just ancillary to it. So those become hotspots. And so reading and aggregating that data. So if it's an order entry table, they might want to slice and dice, aggregate that data quite often. I want to be able to see these orders by sales region, by customer, by salesperson. And so you have all these people taking a finite resource and trying to constantly slice and dice this thing. So, all right, last point here is this is the creative part. So to solve these types of problems, you know, if you've gotten to the point in the project where you made it work right, okay, you're probably a pretty good programmer. You've done everything the right way. You followed all the rules and you've got a nice, good working system. Now, you have performance issues, which means whatever hat you were wearing to get to a system that worked and worked right, you now need to think very differently about how you're going to performance tune. So you need to start thinking holistically. This can be hard for developers that are just in one part of the stack. So a lot of times these have to be people who can see the entire stack from UI all the way down to database because there are changes that might need to happen one place or another that affect the entire stack to try and make this run faster. So this is where you start breaking some rules. Okay? So there are best practices out there. There are best practices for databases. There are best practices for object-oriented design. There are best practices for functional programming. And you want to try and follow all those until you start hitting performance problems. And then you stop being a purist and you start being pragmatic. Now again, you still want to think in the paradigm. You want to try and solve it in the correct paradigm way until it doesn't work, and then you need to start breaking some rules. So at that point, you need to make sure that your team understands, okay, we've got all these policies and procedures that are there that apply 99% of the time to the project. We now need to solve some real world problems. Do I have permission to start breaking and tweaking some rules? So you need to make sure that everyone's cool and happy with that. Try some crazy things. You have this isolated performance environment. You have the ability to blow away your database and recreate it at any time. Start, twisting that box in weird ways. Start thinking about things in ways that don't make any sense, but you feel like you can learn from. And be fearless. Do not be held back by anything that's worked in the past, because you've already incorporated all your best practices and those aren't working, so now you need to start breaking out of some of those and trying different things. So I've found, going back to the creative part, it's interesting that the creative part, that's the part of the project that I've always found. There's two parts. One is the initial design. I feel like I get to be really creative in the initial design. And then the performance optimization part, because I get to do all the weird stuff. Those are sort of when my creative juices get going, because I get to try all kinds of weird things and then objectively be able to show it's better. And that's always cool when you can show people to say, I know this is weird, I know it doesn't make any sense, but yet, look, we've got much better performance. So when you have the evidence on your side, people are willing to pay attention to it. So in summary, know your data so you can partition efficiently. Know how your data is going to change so you know how to manage fragmentation. Know how your data will be used by your app. So make sure you understand how your users are going to use it, how your system ops people are going to be using it, so you can kind of balance all those trade-offs. Knowing your paradigm. Try and work within the design. And then experiment, measure, refactor, repeat. Just get into that scientist mode. And when you're all done and you're all happy and everything works and someone goes, wow, how did you make that work? You just say, it was magic.